So, welcome to the 16th session of the class. Today what I'd like to do is I'd like to try to finish up our discussions on air and then talk about set modifiers. Once we are all set with air and set modifiers, we're going to revisit mixture proportioning to do a little bit of corrections to account for the different admixtures, and then we'll move on and start really getting into fresh properties. So to pick up where we left off last class, we're going to talk a little bit about the effects of mixing and some of the effects of the trucks on air. Obviously, the amount of air that's inside of the system is going to depend on the mixer and depend upon the mixing action, because what we're really doing is capturing the air and stabilizing the air while it's being created. This is going to vary depending upon the speed of the mixing and the amount of time that mixing is occurring for. And one of the other things that I would say is it's not uncommon to see quite a bit of variation between the air content that we would have during the mixing process and when it shows up on site. There's usually a pretty big variation. Usually there's about 1 or 2% drop in the overall volume of air, although this can be higher, especially in cases where you've got hot weather conditions where your concrete is setting up. Now, I think we left off with this graph last time, and I said this is one of the graphs that I find most interesting, because one of the things that I was always baffled by as a materials inspector when I worked for the DOT is why we could only put 300 revolutions on a truck. And it seemed to be this magic number where you could only let the barrel of the truck revolve 300 times. And those types of numbers start to come out of data that's here. Normally when the truck is actually mixing, you'll see it doing something like 18 revolutions per minute as it's driving down the street and passing you. When you see one of these ready-mix trucks passing you on the road, if you stop and you watch the number of times that the hatch goes around, you'll see it's somewhere around 2 to 4 revolutions per minute as it's traveling down the road just to keep everything moving. But if you look at the number of revolutions and the effect on the air content, what you'll notice is that once you pass a certain point, whether that's 300 or 350, the air really starts to diminish, and that's because you're starting to break down and destabilize this air in the system, and we don't want that to happen when the concrete shows up on site. In addition, we don't want the concrete to lose air due to pumping. One of the things that I will point out is that it's typical to lose 1 or 1.5% on pumping. A lot of times what you'll notice is that steep vertical slopes or vertical drops will cause a big issue. So essentially if the concrete is going to be dropping a long distance, now what we've seen here is not a very long distance on this picture, but if you see the concrete being pushed straight up and then dropping straight down, you wouldn't be surprised to find out that it's going to squeeze out the air when it lands, or it's going to squeeze out the air because we're basically putting it under a hydraulic pressure to be pushing it through this piping system. So one of the things that I will point out, and we'll talk about this a little bit more about placement, it may not seem like the pumping process could affect the concrete dramatically, but it can. And this is especially problematic when we start to talk about air contents in the mixtures. As mentioned, pumping can do very funny things. We will talk about the pump in greater details, but the basic idea is it's going to go through a hopper here, it's going to go through a system, and then it's going to come out the other side and it's going to be placed. The pumping action itself can change the structure of concrete because you are compressing the material and putting under quite a bit of pressure. So occasionally you'll see it breaking down the aggregate, you'll see it breaking down the air inside of the system. The mixing action is again going to be an important component. The drum, if the drum on the truck is worn, you'll see it getting less mixing action, less air inside of the system. Air can be lost during the mixing process, as we talked about, and retempering can cause some problems. One of the problems that we can see that's specifically related to the surface of concrete is this idea of scaling. I've shown a picture here, and this is a picture that's taken from PCA, but the idea of scaling is not the integral freeze-thaw damage that we were talking about before with cracks going throughout the entire system. What we're really seeing here is just sort of the surface of the concrete flaking off. So if we take a second and we look, you'll see that there's some regions here where the surface of the concrete has sort of flaked off, and this is due to freezing and thawing, but it's very specialized near the surface. The way that this is measured is a very sophisticated test. You're going to take concrete, you're going to put it into a box, Put some water on top of the concrete where you've placed that box, and then start to do a freezing and thawing test, and you are going to give it a number between 0 and 5. So it's kind of like testing on American Bandstand. 0 means it doesn't look like anything happened in the surface. If you go up to something like this, you can see the majority of the surface is scaled off, and this is sort of the ASTM approach that's used. In general, as you add air content to the system, scaling goes down, but there are a few things that I will point out that are really specific to scaling. This is a very, very, very severe test. There are a few things that make this test incredibly severe. One is we are going to use a concentration of the salts that are intentionally severe. It turns out that if you use a very high concentration of salts, it's not as bad. Very low concentration of salts, it's not as bad. Sort of a medium concentration of salts, 3, 4, 5%, are generally the worst salt contents for scaling. Here you can see the slab that's been created. It's sitting in containers that look like they were stolen from McDonald's. They weren't. We actually paid for those, so don't get any ideas next time you go to McDonald's. And then there's a pond that's created on the top and solution placed in the top surface. Now, as I mentioned, one of the issues with this is the idea that you're sort of rating things based on a visual inspection. And if you look at these surfaces, this is sort of the best possible case scenario that you would get to distinguish between the surfaces, and I don't think it's surprising to anyone that if 3 of us walked in and looked at a concrete that is somewhere in this range, we're going to see different numbers. And you might get a 2, I might get a 3, somebody else might get a 4, depending upon how they look at it. So one of the things that people have tried to do is come up with a more quantifiable way to do this. One of the methods is to measure the scaled weight that comes off of these samples. So every 5 cycles, to collect the particles that are coming off of the surface, to dry them out and to weigh them, and then typically they'll set a limit. Usually the limit's about 1 kilogram per meter squared, 0.8 kilograms per meter squared, somewhere in here. Basically, if you're below that level, it's not much of a problem. One of the things that I will point out that's incredibly important, this particular test is very sensitive to the way that the concrete is finished. It's very sensitive to if it has a lot of bleed water, and I'll show why in a couple seconds. The other thing that it's very sensitive to is the thickness of the sample. And it turns out that the thickness of the sample controls quite a bit about the freezing rate of the concrete, and if you get a sample that's a little bit thicker, it doesn't freeze quite as fast and is less likely to scale. There's some recent work that's coming out of Princeton, some of the work that's coming out of George Shearer's group, that also says the surface the friction of the surface may have a big role on how much scaling is taking place. And what George has been looking at is the fact that the ice doesn't freeze uniformly across the top of the surface of the system. So what you're going to get are pockets of brine that is not frozen. You're going to get pockets of ice, and where the ice grips on, it's going to sort of pull that top surface off. A few years ago we did a study. This is particularly problematic when we start to talk about supplementary materials. So you'll see on the bottom there's a very cryptic nomenclature down here. C, that's simply our cement system. F1 is a fly ash, S is a slag, and then F2 through F4 are different types of fly ash. And one of the things that we were looking at in this particular study was the effect of curing of the system. So there's a little bit of belief that if you've got a curing compound on the system, you won't get scaling to happen. This is a typical white pigment curing compound, comes from the Meadows Company. And what you'll notice is these are the exact same concretes prepared the exact same way, and the difference between having no curing compound or a curing compound on the sample is pretty marked. You don't see this green line is that limit that I was mentioning before. You see that there are a couple that may scale if they go above that limit, but they stay below when you've got the curing compound on. Now there are 2 reasons for this. One, the curing compound is going to increase the slipperiness of the surface, so it's more difficult for the ice to bond and pull off that top surface. The other is that curing compound is probably preventing moisture from getting into that porous surface up at the top of the concrete. One of the things that we noticed, and one of the reasons why this is particularly problematic when we start talking about supplemental materials, is the fact that your surface is not going to be as dense as the rest of the concrete. And we'll talk about this later when we start to talk about the concept of bleeding, but essentially your fly ash particles are fairly light, want to float. Your slag particles are a little bit light, and what you will see if you take a scanning electron microscope image, you will see that inside of the core of the concrete it tends to be much more dense toward the top surface, the system doesn't necessarily get as dense and there's a lot of holes or porosity. So if we just look at the image to segment out the porosity, you can see that the bottom has quite a bit more white or hardened material than the top surface does. So there's a lot more porosity at the top surface. It's a lot easier for water to get inside of the system. One of the things that we actually looked into was the idea that you could reduce the porosity on the top surface by applying a little bit of a gentle drying that's taking place on the top. If you apply a little bit of gentle drying on the top surface, what will happen is the capillary forces will actually pull the particles together. You'll de-water the top part of the system and you'll make it much more resistant to scaling problem. Some of the test methods we'll talk about for air entrainers. There are several different tests that can be performed. Some are performed on fresh concrete, some are approximate, some are performed on hardened concrete. I'm going to go through these fairly quickly, and I'm going to point out the fact that we still don't have a really good test for determining the air content of concrete. And there are a few reasons for this, which we'll try to hit as we go through. The simplest is one of my favorite tests, and it's the ye old bucket test. So every time Purdue plays Indiana, we talk about the old oak and bucket game. This is the old oak and bucket type of test where we have a very standard test, and all we're doing here is measuring the density of the concrete for a specific volume. So we're essentially measuring the yield of the concrete. It gives you an approximate measure of the air of the system. It's within about 1 or 2% accuracy, but it's a pretty good rough test to take, and many times this is a simple test to take because you've got to fill up a bucket anyway to do any of the other tests, so you may as well just monitor the yield or monitor the overall density of that concrete in the system. So the basic idea is you're going to compute the air by just taking 1 minus the actual density over the density of the components that are inside of the system, and that gives you an idea of the volume of the air that's inside of the system. The method that's probably the most common method to get air is called the pressure meter. This is ASTM C231. It's based on a change of volume before and after the system is pressurized. In other words, this is simply Boyle's law. The basic idea is concrete is going to be put into this measuring bowl, and the measuring bowl is really on the bottom portion of the system down here. In the cartoon, it's this bottom portion down here toward the bottom. Water will be added above the system. The level of water will be measured before and after pressure, and the basic idea is that you can pressurize the water to go into the air-filled spaces, and you'll get an idea of what the difference is between when you've got the pressure applied and the pressure released, and that'll tell you the amount of air in the system. Now, there is one big caution in using this test. You cannot use it when you've got porous aggregates. So if you've got something like a slag aggregate, you've got something like a lightweight aggregate, this test will not work very well. It also will not work very well at high altitudes because the pressure needs to be corrected. So you need to calibrate this particular method. One of the problems of both of these techniques, the first, the gravimetric technique, is very, very approximate. The second technique still has about a 0.5% to 0.75% variation in air. Neither one of those techniques, however, gives you a size distribution of the air bubbles. So there has been quite a bit of work to try to get a little bit better idea of how big the air bubbles are, how many of the air bubbles there are. Remember, we talked about the idea that we didn't just want one great big air bubble. We wanted a relative distribution of the air bubbles. So there's something that's been referred to as the automated air meter, or the Danish air void air meter. The basic idea here is you're going to use this thing that looks like the world's weirdest looking bazooka down here, and you are going to take a sample of cement mortar or cement paste out of a system. You will then place this into a viscous medium, kind of like a waterish type media, and the basic idea is that the size of the bubble will cause it to rise out of these specimens at different times. So big bubbles will rise, they will leave the specimen, they will come up through the tube, and they will be collected underneath a plate. And as these air bubbles are collected underneath that plate, they're going to make the plate seem lighter, so we can actually measure a weight of air, believe it or not, because we're measuring the air that's pushing up on that plate. And the basic idea is we can relate the size of the air bubble to how fast it comes out of the sample, and we can collect these under a buoyant device. There are a lot of people who are trying to use this right now. The big benefit here is you can do this on a fresh concrete. You can get the information in about 20 minutes. You can get the distribution of the air content. One of the little problems is This needs an incredibly stable surface to be doing it on, so if you're in a laboratory, it's real easy to do. If you're out in some sort of a job trailer and something is jiggling outside of the job trailer, it's jiggling the air out of your system and can throw off some of your results, and that can be a little bit of an issue. The test that's sort of the gold standard, at least for right now, in how to test for air is the ASTM C457 test method. Here we can see a picture of some fairly old equipment that's been used to do this, but the equipment itself hasn't changed much except for the automated type methods that are out there. The basic idea here is we're going to polish the surface of the concrete. So this is a surface of the concrete that's been cut with a diamond saw. The surface is then going through a series of grinding with different levels to make it as smooth and flat as possible until we get a surface that looks like this one over here, where you can start to see some of the air bubbles. The basic idea is that you'll see the surface of the concrete. There'll be an air bubble, and in theory the air bubble should simply just be the size that it was originally. Sometimes if it's not prepared properly, you can get this little edge to knock off of the system, which can give you some erroneous readings. So you need to be especially careful when you're preparing the samples. So the cylinders are cut. They're either cylinders or they're sections of beams. They're polished. They're placed on a lapping wheel to grind them. They're typically final polished on a glass plate with a very fine grinding powder, and then they're going to be magnified 50 to 125 times. The basic idea when you look at this under the magnification is you are going to be going through and you're going to be counting. You're going to be doing a traverse across the specimen, and you're going to take about 1,200 points. You're going to look through the microscope, and you're going to look here, and you're going to say, that looks like it's paste. And then you're going to move over, and you're going to get a next point, and you can say, that looks like it's aggregate. And if you do this about 1,200 times, and you keep a collection of all the times you went ooh for paste and for aggregate, you can get a relative distribution of the aggregate's paste and porosity in the overall system. Now, unlike what I've shown here where we actually have the grid placed across the top of the system, in the actual test, the entire thing is on what's called a Roswell traveling table. So the microscope stays constant, and you're going to be moving the sample back and forth underneath it, with each turn of the table being usually about 1/10 of an inch of movement. I'm going to skip some of the things on spacing factors and point counts, and I'm going to jump ahead and start to talk a little bit about our set modifying admixtures. Any questions before we go to the world of set modifying admixtures? Sometimes we need concrete that sets a little bit faster. You can see an example of the concrete that's needed over here. I think the motorcycle driver, I'm assuming that's a motorcycle, not a snowmobile. You can see that he would have liked the concrete that set a little bit faster. Sometimes the concrete is maybe set too fast or is a little bit too hard, and it's going to crush the surroundings around it. Or maybe the driver just needs to make sure that the truck fits to where it's being placed. But the basic idea is what we're looking at is frequently, because of the fact that concrete is going to be placed at different temperatures under different environmental conditions, we want concrete that's either going to set faster or it's going to set slower. So what I want to talk about today is I want to talk a little bit about this idea, the rate of heat developed. I want to correlate that with some of the types of construction operations that we might do. Talk a little bit about the effects of temperature on hydration. We haven't spent a lot of time talking about that up to this point. Then talk very briefly about accelerators, retarders, and then the idea of the hydration stabilizers. And once we finish this, as I mentioned, the next thing that we're going to voyage off into is mixture proportioning. We're going to come back to mixture proportioning with a few examples. And what I will do is I will show you how we can make adjustments for the admixtures in the overall system. Now, you'll remember that we had a curve that looked something like this just a few weeks ago. This was the dQ/dt curve, and dQ/dt was talking about the rate of heat evolution. Now, why was this important? What is the rate of heat evolution telling us about? Degree of hydration, telling us how much of the reaction has taken place, and it's also telling us a little bit about when the concrete starts to set. So the concrete is going to start to set sometime after we go from region 2 here up to region 3, and this is going to be incredibly influenced by the temperature of the overall system. To relate this back a little bit to some of the construction operations, what I've done is I've placed this, again, it's going to be a log time scale plotted along the bottom x-axis. We're going to have the rate of heat evolution plotted here along the y-axis, and then you'll see some different points that keep popping up, so we can go through this fairly quickly. But during the batching phase, here you can see the concrete being mixed in a central plant. Once it's mixed, it'll be dumped into the back of a truck. Now this is slip form paving, where it's going to be centrally mixed, hauled out to the job site. This is where we're getting that initial spike, that rapid heat release that's happening during the first 10 to 15 minutes. While the concrete is being transported in the world's cleanest truck, I don't know where Tony got this picture, but this is the world's cleanest truck to be taking concrete out to the construction site. What we'll notice is this is where the concrete is really in this dormant phase. The concrete really isn't doing a whole lot. There's not a lot of reaction going on, and this is what keeps the concrete able to be placed when it gets out onto site. We want to be placing the concrete while it's still in the dormant phase, and here you can see it going into a paver. The paver has crawlers that are moving down the side, moving along on the subgrade. This is the edge of the slip form paver, and the basic idea is we're going to be moving some of this material. Now this is a very low slump material. It's going to be pushed out in front of the paver. It's going to be spread in front of the paver. There's usually a screw auger in here that's simply making sure the material is kind of knocked off and being relatively uniform in front of the paver. Once that happens, we're going to start to vibrate the system, and it's going to be slip form paved out the other side of the system. So on the other side, we're going to see this is what the finished product looks like. You'll notice that there's no formwork because the idea was the energy is supplied in the paver, liquefies the system, gets things moving. During that point, the paver itself has some edges. So if you look really closely here, this is the formwork that's on the side. The basic idea is that once you've passed and the vibration has left the system, it's going to remain in this new shape. So here you can see that they're going to start the overall finishing process here, and this is, you want this to happen before the temperature starts to rise, before the temperature starts to go up. Basically because now the concrete is going to start the process of going through initial set. They're going to be placing the curing on during this period, and there's going to be rapid hydration taking place during this period. Curing compound being sprayed across the surface, the curing compound being white here so that you can tell where it is and so that it'll reflect a little bit of energy. And then typically you'll start to see the temperature or the heat release going down, and that's typically when we're getting on the concrete to be doing things like saw cutting and other types of construction operations. So what are some of the effects of temperature? If we jump in there, here's a pretty graphic example of temperature to sort of remind us that it can be incredibly important. In the 1970s, there was a multi-story building being constructed at a place called Bailey's Crossroads in Virginia. It was a 26-story project that was being constructed incredibly rapidly. It was being done in the late fall construction season. Concrete was being placed on the 24th floor while the shoring was being removed on the 22nd floor. So the basic idea is the formwork would stay in place on the 23rd floor. They would take it out on the 22nd floor so that they could start to move it up to the next, the 25th floor. And at one point there was a sudden progressive collapse. And here you can see a picture of that sudden progressive collapse that basically took the concrete on those floors and all the floors below it out. This obviously has a significant impact because of the lives that are impacted by this. There were quite a few fatalities, quite a few injuries through this, and the basic overarching issue here is that when concrete is at a colder temperature, it does not set as quickly, doesn't gain strength as quickly, and this can be very, very problematic. And this is frequently seen, especially in the late fall construction season, that we need to be cognizant of the fact that concrete is going to react more slowly. It's going to set more slowly. So colder temperatures are going to cause the cement to hydrate in a more slow fashion, set in a more slow fashion. The concrete can lose moisture and heat very rapidly at this time. One of the things that we frequently overlook, you'll hear people talk about wind speed quite a bit when it comes to moisture loss because that'll take water out of the system. But air across the top of a pavement can really have quite an impact on the temperature loss of the overall system as well. You have to protect the concrete from early freezing. If it freezes too early, it can cause a big problem because ice can start to push the hydrated products around. And frequently you'll see people requesting different things to keep the concrete from not experiencing freezing problems at very early ages. Here are a few of the different options and some typical dollars associated with this. A heated mixture, this is something that's fairly common in the Lafayette area here. You'll notice if you drive by 65 at various times during the year, you will notice that there is heat coming out of the aggregate bins. They're actually going to heat up the rocks before they place them into the back of the truck. They'll heat up the water, and that'll cause the concrete to be a little bit warmer when it's placed. Type 3 cement, or a high early strength cement. Type 3 is mostly going to be made in this region by grinding the cement finer. Sometimes you'll see extra cement going in the system. The basic idea here is extra cement is going to give off more heat. Water reducers that we've talked about before, lower water to cement ratios, blankets or heaters being used, and what you'll see is each one of these comes with a certain value associated with it. There's going to be a premium paid to get this to happen in the overall concrete. I will point out a picture, and I don't know why my mother let my father put this, or my father let my mother put this wallpaper up inside the house. I know it's not there right now. But one of the things that contractors don't like to do is they don't like to spend extra money on these types of processes unless they have to. Similarly, though, if concrete is too hot, it's going to sit too quickly, and we're not going to have time to place that concrete. So you'll see, especially in very warm weather regions, you'll see them putting either dry ice into the back of a truck to cool down the overall materials, or actually replacing the water in the system with ice so that they can cool down the overall temperature of the mixture, keeping the aggregate saturated, keeping down the overall temperature of the mixture. So at higher temperatures cause the concrete to hydrate faster. This can be a problem because the concrete may get away from the crew. If you hear them talking about it getting away from them, that means that it's set up too quickly. They didn't have time to finish it properly. You can also see excessive evaporation sometimes taking place, where plastic shrinkage cracking can really be an issue. And one of the biggest issues here is if it's really hot during the day, the temperature drops down at night. That is sort of that is really symptomatic of where you're going to get a big problem. If the temperature drops very quickly at night, the surface of the concrete is going to be very cold. The core of the concrete can be very warm. That temperature differential in the concrete can cause it to crack just on the temperature in the system alone. Typical rule of thumb is something around 18 degrees is a significant enough temperature difference that can cause cracking in just about any mixture. Question, Mike?
Is that why they do slip-form paving like really late at night, so it has the highest heat at the beginning and kind of carries it through the night into the day, and then it warms up again?
There is a lot of discussion of changing the times that they do certain construction operations. For example, bridge decks or paving they may do later in the day so that they can optimize some of these temperatures. So that's one of the reasons that they're going to do that. There are some other issues because it tends to get windier at certain times of the day than others, and other things like that. But that's one of the things that they'll try to do. Night placements will minimize evaporation and minimize temperature effects. Other questions? Okay, if we start to look at the relative development of strength, this is some data from the 1950s, but there's no reason why we would think this would be anything that wouldn't be similar to what we would see today. Zero strength, obviously, down here. 100% of the overall compressive strength at 28 days would be shown here. And here you can see plots of the concrete stored at different temperatures and how rapidly it's going to gain that 28-day compressive strength. Very low temperatures, it's going to take a long time to start gaining that compressive strength. Sort of normal room temperatures, 21 degrees, going to take a little bit less time. If we start heating the system up to about 38 degrees, it's going to set and harden very quickly. We're going to develop strength very rapidly. Now, one of the things that we can start to point out, and I'm going to start to try to look at this is going to look at the strength developed at two separate ages. So here we have the compressive strength developed as a function of curing temperature at 1 day. And the basic idea here is simply chemical reactions are going to take place faster when the system is warmer. This is the same thing you saw in chemistry class. This is the same thing that causes your grass to grow faster in June than it did in the end of March. The faster the system, the faster the reaction, the higher the temperature. So we're going to see that here. The higher temperature, faster the reaction. The basic idea here is at high temperatures, we would get a lot higher strength because the system is simply reacting faster. in theory, all these materials should get to the same long-term strength. Unfortunately, that's not necessarily the case, and what we can sometimes see is that at longer times, this trend starts to reverse itself. And this is a little bit harder to describe because you would say, well, the temperature's been hot, the whole system should be hydrating. Why doesn't it just get to a single value, where it's flat at some long term? Why would a material stored at a higher temperature, why would that have a lower overall strength? Well, this is really likely due to the fact that at really high temperatures, the system is hydrating so quickly that it doesn't have time to form a really good microstructure with a really uniform system of hydrated products. And an example of this we can see up here in the top corner, and most of you have played a game that looks something like this. Tetris. All right, and you start off and you are the world's greatest Tetris player on screen one because being an engineer, you are so good with geometry that you can wiggle all these things around to form a nice, solid, dense structure and score lots of points in Tetris. When you get up to level 17 and these things are just shooting down from the top very, very quickly, the system you don't have enough time to make the system as dense as it possibly is, and you start seeing some of these holes inside of the system, and those holes that are forming inside of the system, that variability is porosity, and that porosity can control the long-term strength. So one of the things we have to be really, really careful about is if the temperature is too hot, what we're going to see is in these really, really hot systems, we are going to see the fact that our concrete is not going to be gaining the strengths that we expect it to be gaining. So what can we do to start to come up with a way to combat the effects of temperature? There are a series of different types of admixtures. We've already talked about water reducers and air entrainers. However, now we're going to talk about admixtures that can be used to modify the setting of the concrete. These are going to be controlled by ACI 212, the Committee on Chemical Admixtures. Accelerators obviously are there to sort of play the role of the rabbit. They are there to make the reaction take place more quickly. Retarders are there to sort of play the role of the turtle. They're there to make the system go a little bit more slowly, delay the overall reaction. So as mentioned, an accelerator is there to increase the rate of hydration. Typically you'll see this as a type C admixture or a type E admixture when it's used in conjunction with a water reducer. The applications are to maintain normal setting if it's a cold temperature type of environment, or to increase productivity by shortening the time that the concrete is going to be in the forms. If you're in a precast type of application where you want to try to turn those forms over quickly, you can use an accelerator to do that, or to compensate for strength gain when we're using some of those supplementary materials, especially when these are being used at colder temperatures. An accelerator can help to kick off the overall system. So as mentioned, generally we're talking about type C accelerators. Generally these admixtures are related to the rate of reaction of the C3S. However, I will point out that in repair and in some of the shotcreting applications, shotcreting basically being like spraying a cement paste or a cement mortar up on a wall, they will work not necessarily on the C3S. They'll work typically there on the C3A because you're trying to get the system to stiffen up between the time that it shoots out of the nozzle and the time it hits the wall. And the C3A is going to be reacting the most quickly. Our typical accelerators are acting on the C3S, and generally they're not going to have much of an effect on air entrainment. It's just going to cause the entire system to set more quickly. So as we were talking about last class, setting time is going to be dictated by the conventional test of poking the concrete with some sort of a magical stick. When the stick starts reaching a level of resistance, we will denote one level of resistance, the limit of handling on the overall system where it's no longer a fluid. We will refer to that as initial set. Where all of a sudden we can start having people walk across the system, we will say that it's undergone final set, and these correspond roughly to the time where someone can start walking across the surface and leave about 1/8 of an inch divot in the top surface, and these are correlated to the times where finishing operations are going to start to take place. So what I'm plotting here is simply on the y-axis we've got penetration resistance. This is that magical stick that's being pushed into the surface of the concrete. We're measuring the resistance to that stick going into the surface of the concrete. And on our x-axis, we've got the time. So we're going to be doing a series of tests for different concretes. Here's an accelerator at one particular temperature. So the plain concrete without the accelerator is shown here in blue. When it hits the first level of resistance, we would say it's initial set. Second resistance, we would say that this is final set. And what you can see is as we add calcium chloride to the system is going to start to gain strength much more rapidly. We'd be able to get on and work the system at about 2 hours as opposed to waiting out to 6 or 7 hours for our plain concrete. So this is one type of application of the SET accelerator. Now, calcium chloride is widely available. I would say that it's a widely used material. It's a low-cost material. It's got very predictable performance, and people have a lot of experience with this. It's soluble in both cold and hot weather. It's simply going to add some salt to the overall water of the system. Two problems that you may end up with: it may have a whitish color finish, and you may end up with a little bit of an increased shrinkage. One of the big things that I will point out, though, is when you're putting chlorides into the system, you have the potential to be increasing corrosion. And you shouldn't be using chloride-based accelerators when you've got reinforcing steel in the system. All right, this is something that's incredibly important that you take notice of. Here's a plot simply out of Ramachandran's book, and there's a reference to it at the end of the talk that talks about set time as a function of calcium chloride inside of the system. Now, this is an admixture that was used in the 70s fairly frequently in things like pre-stressed applications, and a lot of those applications went into corrosion very quickly because the chloride was already in the system. So you want to make sure that if you've got a lot of reinforcing steel or you've got reinforcing or pre-stressing steel in the system, you are not going to use a chloride-based accelerator. More realistic way that you might want to use the accelerator is not necessarily looking at it. Here we've looked at it as the calcium chloride dosage. Here what we're looking at is looking at these materials at different temperatures. So if you said I want a material that behaves equivalently to a plain system at 70 degrees, I've got a system that's at 45 degrees. How much calcium chloride would I need to add to the system to do that? You would typically plot these results a little bit differently. Then you could see that if you use calcium chloride, there may be a way that you could start to get these at earlier ages. Here's just a little bit more information that you can see on the different accelerators. I'm not going to spend a lot of time looking at this. Again, we've got sort of the constant strength on our y-axis. Constant strength on our y-axis. We've got the ambient temperature along the x. Some rules of thumb. Admixtures, the reactions when we're using admixtures tend to behave with the Arrhenius law. Now, right now, you're going to say that makes absolutely no difference to me in my life because I have no idea that Arrhenius was even Swedish. I have no idea what he even did. In a few weeks, we are going to talk about the maturity method. So one of the things that we will talk about is the maturity method is based on the Arrhenius law. So whenever you're using an accelerator, you can actually use the Arrhenius law and try to do your calculations. Rule of thumb, every 10 degrees Celsius, for those of you who don't think in terms of Celsius, that's about 18 degrees Fahrenheit amongst friends. For every 10 degrees Celsius or 18 degrees Fahrenheit, the reaction will typically halve or double. So if we go from 73 degrees, we add 18 to that, we would get 91 degrees. Hopefully, we would double the rate of reaction. If we went from 73 degrees, we took 18 off of that, we got down to something like 55 degrees, we would have half the rate of reaction. So now all of a sudden you can start to see that it would take twice as long to react at 55 degrees as it does at 73 degrees. If we go even colder, it's going to take even longer for that reaction to take place. This has a big impact on construction crew operations. If construction crews are trying to move forms or trying to demold forms, they have to be aware of how rapidly the concrete is gaining strength. Because if they're on a 1-week cycle to turn the forms around in July, it's going to be very different than how quickly the concrete's going to gain strength in November. Frequently, admixtures are going to be added to overcome cold weather. Now, I mentioned that chloride shouldn't be used when we've got steel. There are non-chloride-based accelerators. Typically, these will be used In pre-stressed and reinforced concrete, ACI has limits for using these. One of these is something like a calcium nitrate or nitrite. It's very common. It's a non-chloride based accelerator that can be used. You'll also find out that the nitrates or nitrites are going to be used in corrosion prevention or corrosion inhibitors later on, so we'll see that coming up. Retarders, we'll go very quickly through some of the retarders that may be out there. There's a little bit of a difference here between, well, I guess before we jump into retarders, we're going to talk about accelerators and antifreeze. One of the things that I do want to point out here is there is a series of materials that are out there that are not necessarily accelerators, but they are used in cold weather climates. And the basic idea here is these would be used to depress the freezing point of the system while accelerating hydration. So they're going to be used to try to extend the construction period, and here you can see a little bit of a plot of where these would be used. But if you use these, you could get another 120 days of casting in this red region, or an extra 60 days extension of the construction season. The basic idea is these materials are going to depress the freezing point and going to let you cast when it's much, much colder out, especially if you can take advantage of sort of capturing energy that's coming from the sun. Here you can see the concrete being cast. We will talk almost exclusively in this class about how to reduce the temperature that goes into the concrete. This would be a case where you would want to capture as much energy as you could from the sun. So typically you're going to put some sort of a very dark covering over the concrete to try to absorb as much of that sunlight and as much of that solar energy as possible. With that stated, we'll start to jump now into retarders. If accelerators were there to pick up the rate of reaction, retarders are there to decrease the rate of cement hydration. Obviously, we're going to slow the strength development of the system if it's too hot, can lengthen the time of setting, and can be used to offset the effects of hot weather on hydration. Some of the applications, we want to try to eliminate cold joints. Here you're talking about concrete that may be placed, starts to set up. The next batch of concrete comes and is cast on top of it. The two don't really match up or mesh together. In large pours, you may see a retarder being used, especially if it's large or complicated. I will show you an application of this in bridge decks that I think is sort of a novel and interesting application. Can extend the time for placing and finishing the concrete, can reduce the temperature rise at real early ages, can reduce the effects of slump loss. Last class we talked about the fact that slump could decrease quite considerably because those admixtures are, the hydration process is taking place. So if you slow down the process, it'll stay workable, and can enable you to do longer haul times, and this is becoming increasingly important as congestion is increasing around many of these plants. Again, the idea of penetration resistance versus time. If you have no retarder in the mixture, you're going to see this type of penetration resistance curve. You add the admixture, you can see that we're going to delay the time of initial set, delay the time of final set, and that's really what we're wanting out of these mixtures. Sugar is a fairly typical type of retarder, or the derivatives of sugar. You'll also see some lignosulfonates, some hydrocarboxylate derivatives. You'll also see some things like phosphates being thrown into the system. Again, they're typically going to work on the dormant period of C3S. They're going to extend that out a little bit. They will limit the growth of the calcium hydroxide, and typically the growth of the calcium hydroxide is really what signals the end of the second region and kicks us up into the third region. Their interaction with C3A is going to be much more complex than what we've talked about before for some of the other admixtures. I'm not going to spend a lot of time on this. You will see some of these being used with type K admixtures because of these interactions. Type K we will talk about is a special type of cement that actually undergoes a massive expansion at very early ages. The effects of a retarding admixture on workability. What I will point out here is it depends a lot on the admixtures that you're using. You can see that one of these graphs shows that the retarder has very little impact. The other shows that it can be substantial. And the reason I point this out is it's going to depend entirely on the admixture that you're using, and it's going to depend entirely on the system that you're using. So some will help you increase set time, not reduce slump loss. Others will not be as helpful. I've given you the two references here. This is out of Dodson's book. Again, the reference is given at the end, and this is out of a paper by Whiting and Dysdek. One of the other types of applications where these are starting to become more and more popular is the use of retarders for surface treatments. Here in the bottom corner you can see an exposed aggregate type treatment. The idea here is that the admixture wouldn't be integrally mixed. It would not be integrally mixed. What you would have is the concrete would be placed and then you would come by with sort of a sugar solution to spray on the surface. What this would do is it would keep the top surface from hardening, and then you could come back later on after the rest of the concrete is hardened and spray off the top surface of the paste. By doing that, by spraying it off or scrubbing it off of the system, by scrubbing it or blasting it off or spraying it off, you would expose the aggregate and have a nice exposed texture. Now this may have architectural aspects of it that we're after. There's also a couple groups that are actually talking about doing this for the surface treatments of roads that make the pavements actually quieter. So sometimes you'll hear them talking about spraying the surface with the citric acid. Citric acid is typically going to be something like this. It's going to help the retarder is going to help to slow down the hydration at the surface where the top surface can be brought off. Other places where you're going to see retarders being used, you'll see retarders being used in mass concreting applications. Now one of the things that I will point out here is mass concrete can mean very different things to different people. If you read your textbook or you read a lot of the ACI literature, they talk about mass concrete, and the one thing that everybody knows that's mass concrete is dams. All right, so everybody gets excited, mass concrete dams. What I would point out here is that a lot of times with the high cement contents that we're using for high strength concretes, even things like large columns on bridges can be considered mass concrete. Here you can see a column that's about 12 foot in diameter. If you've got a cement content that's 650, 700, 800 pounds in that system, there's going to be a substantial amount of heat that's being generated. Sometimes you'll see retarders used to really reduce this heat. It enables the pour to go up without control joints. As I mentioned, sometimes if you've got very complicated construction operations, you may want to try to use a retarder. There's a school of thought that's out there that believes that vibration in bridge decks can cause quite a bit of the cracking that takes place at very early ages. The idea is the concrete is relatively fragile. As cars are going by across that bridge deck, it's setting up at different rates, and the cars are causing some vibration on the bridge and can be causing some cracking as the cars are driving by. One way that you'll see retarders being used, occasionally people will start out on one side of the job with one level of retarder, and they'll work their way across the project, reducing the amount of retarder as they work their way across, so that in theory all of the concrete would set at one particular time. So here you can see construction taking place over the White River. I don't know if this was done in this particular construction project. It was just sort of a nice picture. You can see the pumps taking the concrete from the trucks. So the basic idea here is that you would retard the original, the initial concrete that's being placed. The rest of the concrete would be gaining strength much more rapidly, and the idea is that the entire surface, the entire concrete would start to set at about the right time. One of the reasons why people may want to do this is because another reason, in addition to vibration, is the dead weight of itself of a bridge deck is going to be putting stress onto the rest of the deck that's already there. So if you don't get the entire weight of the system on before the concrete sets, you're going to be flexing that very, very fresh concrete. So they want to try to avoid flexing that concrete when they're starting to put more and more weight on from the bridge deck. So this is a way for them to avoid the dead load cracking and reduce the effects of vibration by causing it to set somewhat uniformly. The last thing that I'll talk about very briefly is the idea of hydration control admixtures. I would say this came out in the late 80s and is starting to gain even more and more acceptance. The basic idea here is to use a two-part system. You'll use an activator, which will restart hydration. You'll use a retarder that'll stop hydration. So the basic idea is you'll batch the concrete up. You will throw a retarder in or a stabilizer in that will essentially hold the concrete as being a fluid system until you get to a point where you throw activator in and say start the hydration process again. Here are some concrete trucks. They're roaming throughout the the west of the United States looking for a place to discharge their concrete. They are several hours away from a particular plant. This, I believe, was about an 8-hour haul to get the concrete out there. The idea is when the concrete was being mixed, you throw in the retarder or the stabilizer into the system. When it gets out on the site, they would add the activator to start the overall process. One place where this is being used increasingly is to stabilize wash water and stabilize concrete when it comes back to the plant. All trucks do not come back empty. Frequently, more concrete is ordered than what's needed. If you could add an additive to put the concrete to sleep for the evening, wake it back up the next morning, there's quite a considerable amount of sustainability points that go into that and sort of environmental friendly aspects of that. So here you can see the stabilizer. Basic idea, the reference concrete being shown here in blue, stabilizer would cause it to not do anything until you get to the end of the system. Here's a few comments about modifiers. You can read the summary on your own as we're out of time. Next time what we're going to do is pick up and talk about mixture proportion.
No, I understand. They affect the permeability and overall pores.
Generally, everything else is about the same with the, accelerators and retarders generally don't affect the microstructure a lot. Anything else? I think we're on schedule now. I've tried to go quickly over the last 3 lectures to catch us up. I think we're back on schedule, so that we'll talk about mixture proportion and some of the finer details then, and then we'll start to talk about construction operations.
Good old-fashioned ass whooping today? What? Do you good old-fashioned ass whooping today? No, or you just talking trash? I'm just talking trash.